Welcome. Today we're going to be diving into the fundamental physics behind aviation.
That's right.
Think of this as sort of building our understanding right from the basics, looking at the key principles that actually make flight happen.
Exactly. We'll be looking at, the core physics concepts. These explain pretty much everything from how an engine generates power
Right.
to why an airplane actually stays up in the air. And importantly, we'll see how these ideas don't just describe how things work, but they also let us measure and predict performance, like, calculating exactly how much force an engine is putting out.
Okay, so to get started on this journey, let's begin with the absolute most basic thing.
Yeah.
Matter. What exactly do we mean when we talk about matter?
Well, in simple terms, matter is the stuff that makes up everything. Anything that occupies space has mass.
Okay.
And, well, that we can perceive with our senses. Think about the aluminum in an airplane's body or the jet fuel in its tanks. Those are clear examples of matter.
Got it. The basic building blocks. And there's a really key concept tied to matter, the law of conservation of matter. What's the main idea there?
Ah, yes. This law basically tells us that matter can't be created or destroyed. It can only change from one form to another.
Okay.
A really good example in aviation is burning fuel in an engine. When that gasoline combusts, it seems like it just vanishes.
Right, it just disappears in the process.
But the matter isn't actually gone. It's just undergone a chemical change. It's converted into different gases that get pushed out as exhaust.
Yes.
The total amount of matter stays the same through the whole thing. It's just in a different state.
That's a really crucial point to understand. So matter is the foundation. Now let's look a bit closer at some of its key characteristics. Maybe start with mass and weight. People use those terms almost interchangeably, but in physics, they're quite distinct, aren't they?
Oh, absolutely. Mass is it's a fundamental property. It quantifies the amount of matter an object actually contains. Think of it like the total count of all its little particles. The key thing really is that an object's mass stays constant no matter where it is or its condition.
Right.
Unless, of course, you physically add or remove some matter from it.
So if you have an airplane with a certain mass here on Earth, it would have the exact same mass if you took it to the moon.
Precisely. Now, weight. Weight is different. It's a measure of the force of gravity pulling on that mass.
Okay.
So while the airplane's mass doesn't change, its weight will change depending on how strong the gravitational field is.
Okay, so weaker gravity means less weight, even if the mass is identical. How does that look mathematically? Is there a relationship?
Yeah, there are two main formulas connecting them. First, to find the mass, you can divide its weight by the acceleration due to gravity.
Okay.
Here on Earth, that gravity value is about 32.2 feet per second squared. This actually leads us to a unit called the slug. It's a unit of mass in the English system.
A slug.
Yeah. An object weighing 32.2 pounds on Earth has a mass of exactly one slug.
Oh.
And conversely, if you know the mass, you find the weight by multiplying mass times the acceleration due to gravity. So weight equals mass times gravity.
So that same one slug object would exert less downward force on the moon because the moon's gravity is just weaker.
Exactly right. And this difference, this mass versus weight thing, it also helps us understand why astronauts seem weightless up in the space station.
Right, they're just floating around.
Yeah, but it's not because gravity is zero up there. It's actually because the station and everything in it is constantly falling freely around the Earth.
Ah, so it's like they're in a perpetual state of falling.
Exactly.
Yeah.
Relative to their immediate surroundings inside the station, they experience that weightlessness.
That's a really important distinction. Now, another characteristic you mentioned is attraction. This isn't like magnets, is it?
No, not in this context. In
Yeah.
physics, attraction here refers to the fundamental force that exists between all particles of matter. It's a force that tends to pull them towards each other. Sir Isaac Newton's law of universal gravitation describes this force perfectly. It's the same force keeping us on the ground right now, and the same force that dictates how planets orbit the sun. Every single bit of matter pulls on every other bit of matter.
Wow, that's pretty profound when you think about it. Okay, moving on, let's quickly touch on porosity and impenetrability. These sound fairly straightforward.
They mostly are. Porosity just means that matter often has tiny gaps or spaces within it, sometimes down at the microscopic level.
Right.
That's why things can mix, Smaller particles can fit into those pores. Impenetrability, on the other hand, is simply the rule that no two objects can be in the exact same space at the exact same time.
Makes sense. One thing can't occupy the same spot as another.
Precisely.
Yeah, okay, good. Now let's turn to density. I always think of this as how sort of packed together a substance is. Is that roughly right?
That's a good way to think about it intuitively, yeah. More formally, density is defined as the weight of a substance contained within a specific unit of volume. So in the English system, we usually talk about pounds per cubic foot, or lb/ft. In metric, it's grams per cubic centimeter, GCM.
So to figure out the density, we need to know both its weight and its volume.
Exactly. You then calculate it by dividing the weight by the volume. So density is weight volume.
Okay.
For instance, if you have a tank, say 24 cubic feet in volume, and it holds a fluid that weighs 1,497.6 pounds, the density would be 1,497.6 divided by 24, which comes out to 62.4 pounds per cubic foot.
And that number sounds familiar. Isn't that water?
It is. That's the density of pure water at 4 degrees Celsius. And it's often used as a reference point, a standard for comparing the densities of other liquids and solids.
The water is the benchmark for liquids and solids.
Generally, yes. But when you're dealing with gases, you have to be a bit more careful because pressure plays a big role.
Ah, right. Gases can be squeezed.
Exactly. The density of a gas is directly affected by the pressure on it. So, to make sure everyone's comparing apples to apples, standard conditions have been set up for reporting gas densities.
Standard conditions. Like what?
Usually a temperature of 0 degrees Celsius and a pressure equal to 76 centimeters of mercury. That's the average atmospheric pressure at sea level.
Got it. So density depends on weight and volume, and for gases, pressure is key. Now, what about specific gravity? That sounds related to density.
It is very related. In physics, that word specific often signals a ratio, and that's what specific gravity is. It's a way to compare the density of some substance to the density of a standard reference substance.
Okay, a comparison. What's the standard?
Well, for liquids and solids, the standard is usually water, like we just discussed.
Right.
For gases, it's typically air, although sometimes hydrogen is used instead.
So it's like a relative density score. How do you calculate it?
There are a couple of ways. For liquids and solids, you can take the weight of a certain volume of the substance and divide it by the weight of the exact same volume of water.
Okay.
Or you can just divide the density of the substance by the density of water. Same idea for gases, just using air or hydrogen as the denominator.
And what units does specific gravity have?
Ah, that's a key point. Specific gravity is actually a dimensionless ratio. It has no units. It's just a number.
Just a number, okay.
For example, if you have a hydraulic fluid with a specific gravity of 0.8, that just tells you that any given volume of that fluid weighs 0.8 times as much as the same volume of water.
Okay, so if a cubic foot of water is 62.4 pounds.
Right. Then a cubic foot of that hydraulic fluid would weigh 62.4 pounds times 0.8, which is about 49.92 pounds.
So it's a straightforward comparison, heavier or lighter than water or air. And is there a way to measure this easily for liquids?
Yes. There's a device called a hydrometer. It's basically a calibrated glass float inside a bigger glass tube.
Okay.
You pour the liquid into the outer tube, and the float settles at a certain level depending on the liquid's density.
And it has markings on it.
Exactly. The float has markings for specific gravity, and you just read the value where the liquid surface lines up with the scale. Pure water would read 1.00.
So if it floats higher, the liquid is denser.
Right. Higher float means higher density, higher specific gravity. If it sinks lower, the liquid is less dense.
Interesting, a neat little tool.
All right.
Okay, let's shift gears now and talk about energy. We often hear about potential and kinetic energy. What's the basic difference there?
Potential energy is stored energy. It's energy an object has because of its position or its condition. It's the energy it has the potential to release or convert.
Okay, stored energy.
The formula for gravitational potential energy, which is really relevant in aviation, is simply weight multiplied by height.
Weight times height. And the units.
Same as for work foot-pounds or maybe inch-pounds.
So an airplane just sitting on the runway doesn't have much potential energy related to height, but once it takes off and climbs.
Exactly. If you take a big plane like a Boeing 747 weighing, say, 450,000 pounds, and it climbs up to a cruising altitude of, let's say, 35,000 feet, its potential energy relative to the ground is enormous. It's 450,000 pounds times 35,000 feet.
Wow, that's a huge number.
It is. It comes out to 15.75 billion foot-pounds. That airplane now has the potential to do a massive amount of work just by coming down.
Okay, so potential energy is stored, often due to height. What about kinetic energy?
Kinetic energy is the energy of motion. Simple as that. Anything that's moving has kinetic energy.
Energy of motion. And the formula?
The formula is 1/2 times mass times velocity squared. Ke equals 1/2 mv squared.
Okay. mv squared. Weight. Mass, not weight.
Right. Mass. Remember, if you have the weight in pounds, you need to convert it to mass first. You do that by dividing the weight by the acceleration due to gravity, that 32.2 feet per second squared number again.
Got it. Divide weight by 32.2 to get mass in slugs, then use Ke of a count of half Henry. That velocity being squared seems really important.
Oh, it dominates the equation. Velocity has a much bigger impact on kinetic energy because it's raised to the power of 2.
Right.
Think about an Airbus A380 maybe weighing 600,000 pounds during its takeoff roll. Let's say it reaches a speed, a velocity of 200 feet per second. First, find the mass. 600,000 pounds divided by 32.2 feet is roughly 18,634 slugs.
Right.
Then the kinetic energy is 1/2 times 18,634 slugs times 200 feet squared.
That's going to be another big number.
It is. It comes out to about 372,680,000 foot-pounds of kinetic energy.
Whoa.
Yeah. And that massive energy is why you need long runways and really powerful brakes. You have to dissipate all that energy safely when you land.
Absolutely. Incredible amounts of energy involved in just getting moving.
Okay.
That covers potential and kinetic energy. Now let's move into force, work, power, and torque. These all seem very connected. Let's start with force. What's the physics definition?
Force, in simple terms, is basically any interaction that, if you don't oppose it, will change an object's motion.
Okay.
It's the push or pull, the intensity of an impetus that makes something with mass accelerate. Force is really fundamental to understanding work, power, and torque.
And units. Pounds?
Yep, the standard unit in the English system is the pound. In metric, it's the Newton N. 1 pound is about 4.448 newtons. And when we talk about engine thrust, we're talking about force. We use that famous formula, force equals mass times acceleration, ESMA. The result is expressed in pounds of thrust.
Like for a big jet engine.
Exactly, that huge GE 90 or 115B turbofan. It can produce something like 115,000 pounds of thrust.
Yeah.
That's pure force pushing the plane forward.
An incredible amount of push. Okay,
Yeah.
So how does force relate to the idea of work?
Well, in physics, work is done specifically when a force acts on an object and makes it move some distance.
So you need both force and movement.
Yes, absolutely. Both are required. And the movement has to be in the direction of the force. The formula is simple. Work equals force times distance. W equals FD.
And the units are foot-pounds.
Correct. Foot-pounds. FT pound B.
So if I push as hard as I can against a parked 747 and it doesn't move an inch.
You might feel tired, but technically in physics terms, you haven't done any work. No displacement, no work.
Huh. Okay. But if a jack lifts, say, an Airbus A320 that weighs 150,000 pounds and lifts it 4 feet.
Now you've done work. The work done is 150,000 pounds times 4 feet, which equals 600,000 foot-pounds.
Okay.
Or another example. A tow tractor pulling a Boeing 737-800, maybe 130,000 pounds, into a hangar. If the tractor exerts a steady force of 5,000 pounds over a distance of 80 feet, the work done is 5,000 pounds times 80 feet, or 400,000 foot-pounds. Notice something interesting there.
The force is much less than the plane's weight.
Exactly. Because the movement is horizontal, the tractor isn't lifting the plane's full weight. It's mainly overcoming other resistances.
Which leads us perfectly into friction, right? That resistance isn't always just weight.
Precisely. When you calculate work, you have to consider the actual resistance the force is overcoming, and friction is a huge one.
So what is friction, technically?
Friction is a force that opposes the relative motion or tendency of motion between surfaces in contact.
Okay.
And it's kind of a double-edged sword. We need it without friction. We couldn't walk. Tires couldn't grip the runway.
Right.
But it also causes wear and tear and energy loss in machines. There are basically 3 main types.
New types.
Yes. Static friction, which is the force you have to overcome just to get something started moving.
Okay, that initial stuck feeling.
Exactly. Then there's sliding friction, which is the resistance once things are already sliding against each other.
And the third.
Rolling friction, that's the resistance when something rolls over a surface, like a wheel.
Okay, let's take static friction first. That initial force needed to break something loose. How do we figure that out?
The maximum static friction force, let's call it F, is proportional to 2 things. The normal force pushing the surfaces together, which is often just the object's weight F, and the nature of the surfaces themselves. That's represented by something called the coefficient of static friction, usually written as K.
Oh, okay.
So the formula is F equals K times F.
F equals KF prime.
Got it. So, for example, if you have a smooth iron block on a smooth steel surface, the K might be 0.3. If the block weighs 10 pounds, the force needed to start it sliding is 0.3 times 10 pounds, which is 3 pounds.
Okay. So that's why starting a long train is tricky. You have to overcome the static friction of every single car.
Exactly. They often have to apply power gradually to break the static friction car by car.
Makes sense. Okay, so once it's moving, we have sliding friction.
Yes. And sliding friction is usually less than the maximum static friction for the same surfaces.
Oh, okay. Easier to keep it moving than to start it.
Generally, yes. It depends on the materials in contact and that normal force again. But interestingly, the actual area of contact doesn't usually affect sliding friction much.
Really? That seems counterintuitive.
It does, but that's generally how it works.
Okay. And rolling friction, that's where wheels held.
Big time. Rolling friction is much, much lower than sliding friction.
Why is that?
Because the area of direct contact between the rolling object and the surface is tiny compared to sliding. We calculate it similarly, using a coefficient of rolling friction, but M is usually way smaller than K.
Okay.
For instance, a rubber tire on dry concrete might have a rolling friction coefficient error of about 0.02.
Very small.
Yeah. So to keep a, say, 79,600-pound aircraft rolling steadily on a concrete ramp, the tow tractor only needs to exert a force of about 0.02 times 79,600 pounds.
Which is?
Around 1,592 pounds. Compare that to trying to slide it.
Huge difference. Okay, friction is critical.
Yeah.
Now let's add the element of time and talk about power.
Right. Power is all about the rate at which work is done. It's how much work you do in a certain amount of time.
The rate of doing work, how do we calculate it?
Power equals work divided by time. P equals WT. Or, since work is force times distance, you can say power equals force times distance divided by time. P is FDT.
Okay. And the common unit is horsepower.
Yes, horsepower HP is very common. 1 horsepower is defined as doing work at the rate of 550 foot-pounds per second.
550 feet-pounds per second.
Or, equivalently, 33,000 foot-pounds per minute. It's also equal to about 746 watts in the metric system.
Okay, let's use an example. That GE90 engine we mentioned weighs about 19,000 pounds. If we lift it 4 feet, maybe it takes 2 minutes. How much power is that?
All right, first, the work done. 19,000 pounds times 4 feet is 76,000 foot-pounds.
Okay, 76,000 foot-pounds of work.
Now, power is work over time. The time is 2 minutes. So power is 76,000 foot-pounds divided by 2 minutes.
Just 38,000 foot-pounds per minute.
Exactly. Now, to convert that to horsepower, we divide by the conversion factor, 33,000 foot-pounds per minute per horsepower.
So 38,000 divided by 33,000.
Comes out to about 1.15 horsepower.
So even lifting that heavy engine fairly slowly takes over 1 horsepower.
Yep. Shows you why we use machinery for things like that.
Definitely. Okay, last one in this group. Torque. It sounds like work you mentioned, but it's different.
That's right. They can seem similar, but they're conceptually different. Work is force acting through a distance, causing linear displacement. Torque is a force acting at a distance from a pivot or axis, creating a rotational or twisting effect.
Twisting force. Like using a wrench.
Perfect example. You apply force to the wrench handle, which is some distance from the bolt. That force at that distance creates torque, which turns the bolt.
And the units look similar. Inch-pounds or foot-pounds.
Yeah, they often look the same, pound-feet or foot-pounds, pound-inches or inch-pounds. But the meaning is different. Work is force times linear distance. Torque is force times lever arm distance.
Okay, and this is critical for engines.
Absolutely essential for understanding how both piston engines and turbine engines create rotation.
How does it work in each type? Let's start with piston engines.
Okay, in a piston engine, the explosion, the combustion, pushes down hard on the piston.
Right.
That piston is connected to the crankshaft by a connecting rod, but it connects at a point that's offset from the crankshaft's center of rotation.
Ah, like a crank handle.
Exactly. That offset distance is the lever arm. The force on the piston acting at that distance creates a torque, making the crankshaft spin.
Right.
For example, if the force on the piston is, say, 500 pounds, and the offset or crank radius is 4 inches, the torque generated is 500 pounds times 4 inches, which is 2,000 pound-inches.
Got it. Force times the crank radius.
Uh-huh.
And a turbine engine.
In a turbine engine, you have hot, high-velocity gases blasting against the turbine blades.
Ah.
Those blades are arranged around the engine shaft at a certain radius. The force of the gas hitting the blades, acting at that radius from the center of the shaft, generates the torque that spins the turbine and the whole engine core.
So still force acting at a radius, but from gas flow instead of a piston.
Right.
Is there a way to relate torque and horsepower mathematically?
Yes, definitely. There's a direct formula. Torque in pound-feet equals horsepower multiplied by 5,252, and then all of that divided by the engine speed in RPM, revolutions per minute.
Okay, torque HP 5252 RPM.
That's the one. So take a Cessna 172R engine. It might produce 180 horsepower at 2,700 RPM. Plug those numbers in. 180 HP times 5,252 divided by 2,700 RPM gives you about 350 pound-feet of torque.
Okay, that's a clear relationship. So we've covered force, work, power, and torque. Now let's see how we use these ideas with simple machines. What exactly counts as a machine here?
In physics terms, a machine is basically any device that helps us do work more easily or maybe more efficiently.
How do they do that?
Generally, simple machines work in one of three ways. They can multiply the force you put in, they can increase the speed or distance that the force acts over, or they can simply change the direction of the force you apply.
Okay, and we talk about mechanical advantage.
Right. Mechanical advantage tells you how much the machine multiplies your input force or distance. It's the ratio of the output force to the input force.
Output over input.
Or, alternatively, the ratio of the output distance moved to the input distance moved. But here's a key thing. Machines can't create energy. They can't give you more work output than the work you put in. There's always a trade-off.
No free lunch, basically. Okay, let's start with levers. I remember there are different classes of levers based on the pivot point.
Exactly. There are three classes, and it all depends on where the fulcrum, that's the pivot point, the effort, where you apply force, and the resistance, the load you're moving, are relative to each other.
Okay, let's break them down. Class 1.
First class, lever. The fulcrum is between the effort and the resistance. Think of a seesaw or maybe using a crowbar.
Right, fulcrum in the middle.
Right. And depending on where that fulcrum is placed, a first-class lever can give you either a force advantage, less effort to move the load, or a distance speed advantage. The load moves further faster than the effort point, or it might just change the direction of the force.
Okay. Second class lever.
Second class lever. The fulcrum is at one end, the effort is applied at the other end, and the resistance is somewhere in between.
Fulcrum at one end, effort at the other, load in the middle.
Like a wheelbarrow.
Perfect example. A wheelbarrow is a classic second class lever. And this type always gives you a force advantage.
Always multiplies your force. Always. Let's say in that wheelbarrow, the wheel is the fulcrum. The handles where you lift, the effort, are maybe 60 inches away. The heavy load, say 300 pounds, is centered maybe 18 inches from the wheel, the resistance.
Okay.
You'd only need to lift with about 90 pounds of force at the handles. The mechanical advantage is the resistance, 300 pounds, divided by the effort, 90 pounds, which is about 3.33 to 1. You lift with less force.
Nice. Less effort needed. What about the third class?
Third class lever. Again, the fulcrum is at one end, but this time the resistance is at the other end, and the effort is applied between the fulcrum and the resistance.
Effort in the middle. Example.
Think of using tweezers or maybe your forearm lifting something. The elbow is the fulcrum. The weight is in your hand, resistance, and your bicep pulls up in between, effort. Or in aviation, some aircraft landing gear retraction systems can work like this.
Okay. What's the advantage here? Doesn't sound like force.
It's not force. A third-class lever always increases the speed or distance the resistance moves, but you have to apply more effort force than the resistance force. You trade force for speed or range of motion.
Okay. Speed distance advantage, force disadvantage. Is there a general equation for all levers?
Yes, a simple one. Effort E times the length of the effort arm, L equals resistance R, times the length of the resistance arm, L times L equals R times L. The arms are the distances from the fulcrum.
EL covers all three classes.
Yeah.
Okay, moving from levers to pulleys.
Right. A pulley is basically a wheel on an axle designed to support movement of a rope or cable along its circumference. It usually has a groove.
Okay.
The pulley itself is often held in a frame called a block. And when you have a system with multiple pulleys and ropes, that's called a block and tackle.
Block and tackle, okay. What about just a single pulley?
Well, a single fixed pulley one that's attached to a support and doesn't move up or down acts just like a first-class lever with equal arms.
So mechanical advantage of one.
Exactly. It doesn't multiply your force. It just changes the direction you pull in, which can be really convenient.
Makes sense. What if the pulley itself moves with the load?
Ah, that's a single movable pulley. That one acts like a second-class lever. It gives you a mechanical advantage of 2.
Advantage of 2, so it halves the effort needed.
Yes, but there's a trade-off, remember. You have to pull twice the length of rope for the load to move up a certain distance. Force is halved, distance pulled is doubled.
Okay, fixed pulley changes direction. Movable pulley multiplies force. Now, gears.
Gears are essentially toothed wheels that mesh together to transmit motion and force, usually changing speed or torque or sometimes direction.
Different types of gears.
Lots of types. Spur gears have straight teeth parallel to the axis and connect parallel shafts. Bevel gears have angled teeth and connect shafts that are at an angle, allowing you to change the plane of rotation, like from horizontal to vertical.
Okay.
Worm gears involve a screw-like worm meshing with a worm wheel and give you very large gear reductions.
Large reduction,
Yeah.
meaning speed decreases a lot.
Yes, speed decreases significantly, but torque increases proportionally. Then there are planetary gears.
Planetary, like planets orbiting a sun.
Sort of. You have a central sun gear, several planet gears orbiting it, and an outer ring gear. They're compact and offer specific, often quite large, gear reduction ratios based on the number of teeth on each gear.
And the gear ratio always affects speed and torque.
Always. If you gear it to increase speed, torque goes down. If you gear it to increase torque, speed goes down. That's the trade-off, assuming no energy loss to friction.
Got it. Gears manage rotational power. Last simple machine, the inclined plane. A ramp, basically.
Exactly. A ramp is the classic example. An inclined plane is just a flat surface tilted at an angle. It lets you move a heavy object upwards with less force than lifting it straight up.
But you have to move it over a longer distance, right?
Precisely. You're trading increased distance for decreased force. The total work done, ignoring friction, is the same. The same basic lever equation can actually be applied. Effort times the length of the ramp, effort arm, equals the resistance, the object's weight, times the vertical height of the ramp, resistance arm.
Ah, okay. So if you push a 1,600-pound airplane up a ramp that's 24 feet long and rises 6 feet vertically.
The effort needed, ignoring friction, would be 1,600 pounds times 6 feet divided by 24 feet.
Which is 400 pounds. Much less than lifting 1,600 pounds straight up.
Right. And things like screws, bolts, wedges, they're all applications of the inclined plane principle too. A small rotational force over many turns becomes a large linear force.
Clever. Okay, that covers simple machines. Now let's think about what happens inside materials when forces are applied. Stress and strain.
Yes. Stress is the internal resistance within a material to an external force that's trying to deform it. It's like the internal forces the molecules exert on each other.
Internal resistance. And it comes in different forms.
5 main forms, generally. Tension is a pulling force, trying to stretch something apart. Think of ropes in that block and tackle.
Okay.
Compression is a pushing or crushing force, like the force on landing gear when the plane touches down.
Pushing.
Torsion is stress from twisting, like the torque on an engine drive shaft.
Twisting.
Bending is actually a combination. One side of the object is in tension, the other side is in compression. Like an airplane wing bending upwards in flight, the top surface is stretched, tension, the bottom is squeezed, compression.
Tension and compression together.
Okay.
And the last one.
Shear. That's a force trying to make layers of the material slide past each other, like scissors cutting paper, or the force on a bolt connecting 2 overlapping plates.
Okay, tension, compression, torsion, bending, shear. Those are the types of stress. What then is strain?
Strain is the result of stress. It's the actual deformation or distortion of the material caused by that stress. It's the physical change in shape or size.
Stress causes strain.
Exactly. And most materials have some elasticity. They can return to their original shape after the stress is removed, as long as you don't exceed their elastic limit.
Like stretching a rubber band and letting it go?
Precisely. Strain is that temporary change in dimension. Some tools, like certain torque wrenches, actually measure the amount of bending strain in a beam to indicate the applied torque stress.
Ah, using strain to measure stress.
Ah.
Clever. Okay, stress and strain describe how materials react. Now let's go back to motion itself.
Right. Motion is just a continuous change in an object's position over time relative to some reference point.
Okay, and uniform motion.
Uniform motion means constant speed and constant direction, moving in a straight line at a steady pace. Basically, constant velocity.
Which brings us to speed versus velocity.
Yeah.
Used interchangeably every day, but different in physics.
Very different. Yes, speed is just how fast you're going. It's a scalar quantity. It only has magnitude, like 300 miles per hour.
So it's the number.
Right. Velocity, however, is a vector. It has both magnitude, the speed and direction. So 300 miles per hour due east, that's a velocity.
Speed with direction. Okay.
And because velocity includes direction, an object moving in a circle at a constant speed is actually constantly changing its velocity because its direction is always changing.
Ah, okay. Constant speed doesn't mean constant velocity unless it's a straight line.
Exactly. We use vector math to combine velocities, like figuring out an airplane's actual path over the ground when you factor in the wind.
Makes sense. So if velocity is changing, that leads to acceleration.
Precisely. Acceleration is the rate of change of velocity, not just speed, but velocity.
So speeding up, slowing down, or changing direction.
All three count as acceleration. The formula for average acceleration is the change in velocity, final velocity minus initial velocity, divided by the time it took for that change. AVFAT.
Okay. Example.
Sure. Say an F-15 fighter jet goes from 400 miles per hour to 1,200 miles per hour in 20 seconds.
Big speed increase.
Yep. The change in velocity is 1,200, 400 equals 800 mile per hour. The time is 20 seconds. So the acceleration is 800 mile per hour divided by 20 seconds, which is 40 mile per hour per second.
40 miles per hour faster every second.
Right. And we can convert that to feet per second squared, which is a more standard unit. It works out to about 58.7 feet per second squared.
Okay. And we can relate that to g-force.
Yes. 1g is the acceleration due to gravity, about 32.2 feet summon. So 58.7 divided by 32.2 is roughly 1.82 Gs. That's the force the pilot feels pushing them back in their seat.
Feeling heavier during acceleration. Got it. These ideas, force, mass, acceleration, bring us straight to Newton's laws of motion. Absolutely fundamental for aviation, right?
Couldn't fly without them. They are the bedrock of classical mechanics. Let's start with Newton's first law.
The law of inertia.
That's the one. It basically says, an object at rest stays at rest, and an object in motion stays in motion with constant velocity, same speed, same direction, unless acted upon by an external force.
Things keep doing what they're doing unless something interferes.
Exactly. That's inertia, the resistance to change in motion.
Right.
It's why if a plane suddenly stops, you keep moving forward until your seatbelt stops you. Your body has inertia.
Right. Okay, that's the first law. Newton's second law.
The second law quantifies the relationship between force, mass, and acceleration. It says the acceleration of an object is directly proportional to the net force acting on it.
Okay.
It's in the same direction as that force, and it's inversely proportional to the object's mass.
More force, more acceleration, more mass, less acceleration for the same force.
Precisely. And the famous formula, force equals mass times acceleration, FMA.
FMA. Critical.
Absolutely critical for understanding how engine thrust makes a plane accelerate. In fact, we can derive the thrust formula right from FMA. Thrust is basically the mass of air the engine moves per second times the change in velocity it gives that air, exit velocity minus inlet velocity.
Accelerating the air produces thrust.
Yes. Since mass is weight divided by gravity, mWg, we can also write it as force, wg vf/yt. So if a jet engine sucks in, say, 150 pounds of air per second at 100 feet per second and blasts it out at 1,200 feet per second, the thrust would be about 150 pounds, 32.2 feet thus, times 1,200 feet, 100 feet, divided by 1 second, which comes out to roughly 5,248 pounds of thrust.
Calculated right from Newton's second law.
Okay.
And the third law.
The famous one, action-reaction. For every action, there's an equal and opposite reaction.
Equal and opposite.
Always. Forces always come in pairs. When you push on a wall, action, the wall pushes back on you with the same force reaction.
Okay.
In aviation, when a propeller pushes air backward action, the air pushes the propeller and thus the plane forward reaction. That's thrust.
Same for a jet engine.
Same idea. The engine throws hot gas backward at high speed, action, and the reaction force pushes the engine and the plane forward. Lift is also related. The wing pushes air down, action. The air pushes the wing up, reaction.
Action-reaction pairs everywhere.
Right.
Okay, Newton's laws are key. Now, what about motion that isn't in a straight line? Like turning, circular motion.
Right. Circular motion is motion along a curved path with a constant radius. Think of swinging a weight on a string around your head.
Okay.
Now, even if the speed is constant, the velocity is always changing because the direction is always changing.
Right, we covered that. Velocity includes direction.
And since velocity is changing, there must be acceleration. And if there's acceleration, Newton's second law, FMA, tells us there must be a force causing it.
A force required just to keep it moving in a circle.
Yes. This force is always directed towards the center of the circle. It's called the centripetal force, center-seeking force. Without it, the object would just fly off in a straight line, tangent to the circle.
Centripetal force pulls it inward, keeping it on the curved path. Is there a formula?
Yep. Centripetal force, Fc, equals mass times velocity squared divided by the radius of the circle, Fv squared over r.
mv squared over r. Again, mass, not weight.
Right. Use mass, weight divided by 32.2. Velocity should be in feet per second and radius in feet.
Okay. How strong can this force be in, say, aviation?
It can be incredibly strong. Let's take a simple example. Swing a 10-pound weight in a 3-foot radius circle really fast, say 500 feet per second.
That's fast.
Very fast. First, mass is 10 pounds, 32.2 fits, or about 0.31 slugs.
Okay.
Then centripetal force is 0.31 slugs, 500 feet, 3 feet.
What does that come out to?
About 25,833 pounds.
25,000 pounds for a 10-pound weight.
Yes. That's over 2,500 times its actual weight. We'd say it's experiencing over 2,500 Gs.
Wow. That really highlights the forces on rotating parts in engines, like turbine blades spinning super fast.
Exactly. The stresses involved are immense.
Incredible. Okay, let's switch gears again, moving from motion to another fundamental form of energy. Heat.
Right. Heat is a form of energy. It's often defined as energy transferred between systems because of a temperature difference.
Okay, energy transfer due to temperature difference.
It's also closely related to the internal energy of a system, specifically the kinetic energy of all the randomly moving molecules within it. More heat generally means more molecular motion.
So higher temperature means molecules are bouncing around faster.
That's the basic idea, yes. And heat can be generated by converting other forms of energy. Mechanical energy from friction becomes heat. Electrical energy in a heating element. Chemical energy in burning fuel. Radiant energy from the sun. Nuclear energy. They can all be converted to heat.
So compressing a gas makes it hotter.
Yes, because the mechanical work done to compress it increases the kinetic energy of the gas molecules. Conversely, letting a gas expand rapidly makes it cool down.
And friction definitely generates heat.
Absolutely. Rub your hands together. That's mechanical energy turning into heat via friction. The core theory views heat as the total kinetic energy of those moving particles.
Okay. How do we measure heat energy? What are the units?
Two common units are the calorie, with a small c, and the British thermal unit, or BTU.
Calorie and BTU.
1 calorie is the heat needed to raise the temperature of 1 gram of water by 1 degree Celsius.
Okay.
1 BTU is the heat needed to raise 1 pound of water by 1 degree Fahrenheit.
Grams in Celsius for calorie, pounds in Fahrenheit for BTU. Is the food calorie different?
Yes, good point. The dietary calorie, with a capital C, is actually a kilocalorie, or the 1,000 of the small c, physics calorie.
Oh, okay. Important difference.
Yeah.
Which one is used more in aviation?
BTUs are very common in aviation, especially in the U.S. We
Okay.
talk about the energy content of fuel in BTUs per pound, or engine efficiency in terms of BTUs.
Okay. And there's a device to measure this. Calorimeter.
Yes, a calorimeter is used to measure heat quantities precisely. For example, you could burn a known amount of fuel inside it and measure the temperature rise of a surrounding water bath to figure out the fuel's heat content in BTUs.
Measuring the heat released. Is there a direct link between heat energy and mechanical work? Like, can you convert between them?
Yes, there's a very important relationship called the mechanical equivalent of heat. 1 BTU of heat energy is equivalent to approximately 778 foot-pounds of mechanical work.
1 BTU equals 778 foot-pounds. Wow.
Yeah. So think about aviation gasoline. 1 pound of it has about 18,900 BTUs of chemical energy locked inside. If you could convert all that energy perfectly into work, it would be 18,900 BTU times 778 fit-Talby BTU, which is over 14.7 million foot-pounds of potential work per pound of fuel.
Incredible potential. But engines aren't perfect, right? Thermal efficiency.
Exactly. Real engines lose a lot of that potential energy as waste heat through the exhaust, the cooling system, and friction. Thermal efficiency is the ratio of the useful work or power the engine actually produces compared to the potential power available in the fuel it consumes.
How efficient are typical aircraft engines?
Well, a typical aircraft piston engine might only have a thermal efficiency of around 25% to 30%.
So 75% of the fuel's energy is just lost.
Mostly lost as heat, yes. Improving thermal efficiency is a huge goal in engine design.
I can see why. Okay, so a lot of energy is wasted as heat. How does heat actually get from one place to another? What are the transfer mechanisms?
There are 3 main ways heat moves: conduction, convection, and radiation.
Conduction, convection, radiation.
Right.
Okay, conduction first.
Conduction is heat transfer through direct physical contact. Hotter, faster-moving molecules bump into slower, cooler ones and transfer kinetic energy.
Like heat traveling up a metal spoon left in hot soup.
Perfect example. Metals are generally very good conductors of heat. Materials like wood, plastic, or air are poor conductors. We call them insulators.
Okay, direct contact transfer, what's convection?
Convection is heat transfer by the movement of fluids. That means liquids or gases.
Movement of the fluid itself.
Yes. When you heat a fluid, it usually becomes less dense and rises. That rising fluid carries thermal energy with it. Think of hot air rising from a radiator, or water boiling in a pot. The hot water rises, cooler water sinks, creating a convection current.
Okay. Is there forced convection?
Yes, that's when you use a fan or pump to move the heated fluid, like the fan cooling the electronics in your computer. Or, in aviation, air-cooled piston engines rely heavily on forced convection.
Awesome.
They have cooling fins on the cylinders to increase the surface area. The forward motion of the plane, or the propeller blast, forces air over these fins. The heat conducts from the cylinder to the fins, and then the moving air carries the heat away via convection.
Clever use of airflow.
Mm-hmm.
Okay, conduction by contact, convection by fluid movement. What's radiation?
Radiation is heat transfer through electromagnetic waves, like light or infrared waves. It's unique because it doesn't need a medium to travel through.
Doesn't need air or anything, like heat from the sun.
Exactly. The sun's heat travels through the vacuum of space to reach Earth via radiation. All objects with a temperature above absolute zero emit thermal radiation.
Yeah.
And radiant energy can pass through some materials, like glass, without heating them much directly, but then be absorbed by objects on the other side. Think of the greenhouse effect. It also travels in straight lines.
Conduction, convection, radiation. Got the three methods. Now, specific heat, what does that term mean?
Specific heat capacity, or just specific heat, tells you how much heat energy is needed to raise the temperature of a certain amount of a substance by 1 degree.
How much heat for a 1 degree change?
Right, usually per unit mass, like per gram or per pound. It's an intrinsic property of the material itself. Some materials heat up easily with little energy. Others require a lot more heat for the same temperature change.
And water is special here.
Water has a remarkably high specific heat capacity compared to most common substances.
Meaning it takes a lot of energy to heat water up.
Yes, and it also means it releases a lot of heat when it cools down. This is why large bodies of water, like oceans, have such a moderating effect on the climate of nearby land areas.
Yeah.
They resist large temperature swings.
Acts like a big thermal buffer.
Mm.
Makes sense. Okay, let's talk about temperature itself. We measure how hot or cold something is, but there are different scales.
Yes. The three main scales you'll encounter are Celsius, degrees C, Fahrenheit degrees, and Kelvin, K.
Celsius, Fahrenheit, Kelvin.
Celsius is based on water freezing at 0 degrees C and boiling at 100 degrees C at standard pressure. Fahrenheit sets those points at 32 degrees F and 212 degrees F.
Okay, different reference points. What about Kelvin?
Kelvin is an absolute temperature scale. It's 0.0 K is absolute zero, the theoretical point where all molecular motion stops. It's impossible to actually reach, but it's the fundamental zero for thermodynamics. Water freezes at about 273.15 K and boils at 373.15 K.
Absolute zero. Okay, and we can convert between these.
Yes, there are standard formulas. To get Fahrenheit from Celsius, degrees F, degrees 1.8, SJ plus 32. To get Celsius from Fahrenheit, degrees C is degrees F 32, S 59.
Got it.
And to get Kelvin from Celsius, you just add 273.15, or often just 273 for simplicity.
Huh?
K equals degrees C plus 273.15.
Simple addition for Kelvin. Is there rank in 2?
Yes, Rankine degrees R is the absolute scale corresponding to Fahrenheit. Degree R is degrees F plus 460. It's sometimes used in engineering calculations involving gases in the English system.
Okay. Science tends to use Kelvin and Celsius, while Fahrenheit is common in the U.S.
That's generally true, yes.
Now, when things change temperature, they also tend to change size, thermal expansion and contraction.
Exactly. Almost all materials expand when they get hotter and contract when they get cooler. This happens in solids, liquids, and gases.
Do they expand by the same amount?
No. Gases expand the most, liquids are intermediate, and solids generally expand the least for the same temperature change. That's because the molecules in solids are held together more tightly.
Okay, focusing on solids, like in aircraft structures, how do we quantify that expansion?
We use something called the coefficient of linear expansion. It's the property of the material that tells you how much its length changes for every degree change in temperature per unit of its original length.
A coefficient for each material.
Right. The formula for the change in length is L, where alpha is the coefficient, L is the original length, and LT is the change in temperature.
So length times coefficient times temperature change.
Exactly. For example, a steel rod might expand a tiny fraction of an inch for every foot of its length for each degree Fahrenheit rise.
Doesn't sound like much.
It doesn't, but if you have a long structure, like an aircraft wing, spanning many feet, and it experiences a large temperature swing from ground to high altitude, that total expansion can be significant.
And if that expansion is blocked or constrained?
It can generate enormous internal forces and stresses. Aircraft design has to account for this thermal expansion and contraction very carefully, using expansion joints or materials with compatible expansion rates to avoid damage.
Critical design consideration, then. Okay, let's move on to pressure.
Pressure. It's defined as force acting perpendicularly on a surface, divided by the area over which that force is distributed. Force per unit area.
Force divided by area. Units.
Common ones are pounds per square inch. PSI. In meteorology and sometimes aviation, you also see inches of mercury, HG, millimeters of mercury, HD, or millibars.
Inches of mercury? How does that measure pressure?
That comes from the mercury barometer. It's basically an inverted tube of mercury sitting in a dish of mercury. The atmosphere pushes down on the mercury in the dish, and that pressure supports a column of mercury inside the tube. The height of that column, measured in inches or millimeters, indicates the atmospheric pressure.
Ah, the weight of the air balances the weight of the mercury column.
Precisely. Standard atmospheric pressure at sea level is defined as 14.7 psi, and that's equivalent to supporting a column 29.92 inches high.
14.7 psi equals 29.92 Hg. Got it. We also hear about gauge pressure versus absolute pressure.
Yes. Gauge pressure, often written as SIG, is the pressure relative to the surrounding atmospheric pressure. A tire gauge reads gauge pressure. It reads 0 when it's just open to the air.
Okay, pressure above atmospheric.
Right. Absolute pressure is the total pressure, including atmospheric pressure. So absolute pressure, gauge pressure, plus atmospheric pressure.
When would you use absolute pressure?
It's often more fundamental in physics calculations, especially with gases. While most aircraft system gauges, like oil or hydraulics, show gauge pressure, something like engine manifold pressure is often measured in absolute terms because it reflects the actual pressure available to the engine cylinders, including the contribution from the atmosphere.
Okay, gauge is relative, absolute includes atmospheric, and what causes pressure in a gas?
It's all down to the motion of the gas molecules. They're constantly whizzing around and colliding with the walls of whatever container they're in.
The impacts create the pressure.
Yes. The more molecules there are, the faster they're moving, higher temperature, and the smaller the container, the more frequent and forceful those collisions are, and thus the higher the pressure. That's why tire pressure increases on a hot day. The air molecules inside speed up.
Makes sense. And Dalton's law. Something about mixtures.
Dalton's law of partial pressures says that if you have a mixture of gases that don't chemically react with each other, the total pressure of the mixture is simply the sum of the pressures that each gas would exert if it were alone in the same container.
So each gas contributes its own partial pressure to the total.
Exactly. It's related to the proportion of each gas in the mixture, important for understanding air, which is a mixture.
Okay. Pressure is force area, caused by molecular collisions in gases. Now let's get into fluid mechanics, crucial for aviation.
Absolutely. Fluid mechanics studies how fluids, which includes both liquids and gases, anything that can flow, behave, both when they're still, fluid statics, and when they're moving, fluid dynamics.
Liquids and gases, key difference.
A major difference, especially in aviation contexts, is compressibility. Liquids are generally considered incompressible. Their volume doesn't change much with pressure. Gases, however, are highly compressible.
Okay. And fluid mechanics explains things like lift.
Lift, hydraulics, airflow through engines. Many core aviation principles rely heavily on fluid mechanics.
Let's start with buoyancy, that upward push fluids give.
Right. Buoyancy is the upward force exerted by a fluid on any object immersed in it. It opposes the object's weight, making it seem lighter.
And if the buoyant force is big enough, the object floats.
Exactly. An object floats if the buoyant force equals or exceeds its weight. Archimedes' principle is the key here.
Archimedes, what did he say?
He figured out that the buoyant force acting on an object is equal to the weight of the fluid that the object displaces.
Equal to the weight of the displaced fluid. Works for liquids and gases.
Both. The formula is buoyant force expels volume of the submerged part of the object, testitol of the fluid.
Volume times fluid density. Example.
Okay, imagine a 10 cubic foot block that weighs 700 pounds. You put it in water, which has a density of about 62.4 pound at FTA. The maximum buoyant force, when it's fully submerged, would be 10 foot times 62.4 pound of FTA, which is 624 pounds.
So 624 pounds of upward force, but it weighs 700 pounds.
Right. Since its weight, 700 pounds, is greater than the buoyant force, 624 pounds, it sinks. Its apparent weight underwater would be 700 minus 624, or 76 pounds.
It feels lighter, but still sinks. And this explains airships.
Yes. A huge airship displaces a massive volume of air. Even though air isn't very dense, the weight of that huge volume of displaced air can be enough to equal the total weight of the airship, allowing it to float.
Cool. Okay, buoyancy is about displaced fluid weight. What about pressure within a fluid itself?
Pressure in a static fluid increases with depth. That's due to the weight of the fluid sitting above that point.
So deeper means more pressure.
Yes. And interestingly, the pressure at the bottom of a container just depends on the height of the liquid column and its density, not the shape of the container itself.
Shape doesn't matter, only height.
For static pressure at the bottom, yes. We also distinguish between static pressure, due to height depth, and dynamic or ram pressure, which is pressure associated with the fluid's motion, its kinetic energy.
Static versus dynamic pressure, okay.
The total pressure in a moving fluid is the sum of the static and dynamic pressures. We measure this total pressure in places like jet engine inlets.
Got it. Now, Pascal's law. Something about pressure acting equally in hydraulics.
Exactly. Pascal's law has two key parts. First, pressure at any point in a confined static fluid acts equally in all directions. Second, if you apply an additional pressure to a confined, incompressible fluid, that pressure increase is transmitted undiminished throughout the entire fluid.
Transmitted everywhere equally. How does that help with hydraulics?
It's the foundation. Because pressure-force area, or force-pressure-S area, if you apply a small force to a small piston, small area, you create a certain pressure in the hydraulic fluid.
Okay, pressure, small force, small area.
That pressure is transmitted everywhere. If that same pressure then acts on a much larger piston, large area elsewhere in the system, the output force on that large piston, pressure S large area, will be much larger than the input force.
Ah, you multiply the force. Yes. Apply 5 pounds to a 0.5 square inch piston, you get 10 psi pressure, 5.5. If that 10 psi acts on a 5 square inch piston, the output force is 10 psi 5 n's equals 50 pounds. You turn 5 pounds into 50 pounds.
That's the magic of hydraulics. But there's a trade-off, right? No free work.
No free work. You gain force, but you lose distance. The larger piston moves a proportionally smaller distance than the smaller input piston. The volumes moved are equal. Input area X, input distance, output area X, output distance.
Force goes up, distance goes down, work in equals work out, ideally.
Exactly. It's a force multiplier used everywhere in aircraft for brakes, landing gear, flight controls.
Okay, Pascal's law for hydraulics. Now, Bernoulli's principle, this is the big one for lift, right? What does it say?
Bernoulli's principle essentially states that for a fluid in motion, where the speed increases, the static pressure decreases, and vice versa. This assumes no energy is being added or taken away along the flow path.
Faster flow, lower pressure. Slower flow, higher pressure.
That's the core idea. Think of a Venturia tube, a pipe that narrows in the middle and then widens again. Okay.
As the fluid flows into the narrow section, the throat, it has to speed up. Bernoulli says its static pressure must drop there. As it flows into the widening section, it slows down, and its static pressure increases again.
Speed and pressure are inversely related. How does this create lift on a wing?
An airplane wing's airfoil shape is designed, crucially, so that the air flowing over the curved top surface travels a longer distance than the air flowing under the relatively flatter bottom surface in the same amount of time.
So the air on top has to go faster.
Exactly. And according to Bernoulli, that faster-moving air on top exerts lower static pressure than the slower-moving air underneath the wing.
Lower pressure on top, higher pressure on the bottom.
Creates a net upward force. That pressure difference, acting over the whole area of the wing, is lift.
Amazing. Just the shape of the wing makes the air speed up on top, pressure drops, and it gets sucked upwards.
That's a good way to visualize it. It's also used in carburetors. The Venturi effect creates low pressure to suck fuel into the airflow. It's fundamental to subsonic flight.
Bernoulli, faster flow, lower pressure. Got it.
Yeah.
Okay, let's switch to sound now. What is sound physically?
Sound is basically a disturbance, a vibration, that travels through matter, a medium, like air, water, or solids, as a wave.
A wave traveling through a medium. What's needed for sound?
Usually 3 things. A source to create the vibration, like vocal cords or a tuning fork, a medium for the wave to travel through, and a detector to sense it, like our ears.
Source, medium, detector. How does the wave work? Like water wave?
Water waves are a good visual, but they're typically transverse waves. The water molecules move up and down perpendicular to the direction the wave travels.
Okay, sound waves are different.
Yes, sound waves in air are longitudinal waves. The air molecules vibrate back and forth parallel to the direction the sound wave is moving.
Parallel. How does that work?
Imagine hitting a tuning fork. As the prongs vibrate outward, they compress the air molecules nearby. High pressure region, a compression. As they move inward, they leave a region of lower pressure, a rarefaction.
Compressions and rarefactions.
Right, and these compressions and rarefactions travel outwards from the source as the sound wave, even though the individual air molecules just oscillate back and forth around their starting positions.
The wave moves forward, but the air molecules just wiggle.
Got it.
Does sound have a specific speed?
Yes, in a given uniform medium under specific conditions, sound travels at a definite speed. But that speed varies depending on the medium, its density, elasticity, temperature.
Travels faster in solids, slower in gases.
It's generally yes. Fastest in solids, slower in liquids, slowest in gases. And temperature really affects the speed in gases like air.
How fast in air?
At 0 degrees Celsius, 32 F, the speed of sound in dry air is about 1,087 feet per second, which is around 741 miles per hour.
Okay. Does temperature change that?
Yes, it gets faster as the air gets warmer. The speed increases by about 2 feet per second for every degree Celsius rise, or about 1.1 hepes per degree Fahrenheit.
Faster and warmer air. What about the characteristics we hear, like pitch and loudness?
Pitch, how high or low a sound is determined by the frequency of the sound wave, how many compressions pass by per second. Higher frequency means higher pitch.
Okay. And loudness?
Loudness is related to the amplitude of the wave, how much the air molecules are displaced from their rest position. Bigger amplitude means a louder sound, more intensity.
Frequency is pitch, amplitude is loudness. What's resonance?
Resonance happens when you have an object that has a natural frequency it likes to vibrate at. If a sound wave hits it at that exact frequency, the object can absorb energy very efficiently and start vibrating with a really large amplitude.
Like a singer shattering a glass.
That's a classic example, yes. It's also why pilots might avoid certain engine speeds, RPMs, if they cause resonant vibrations in the propeller or airframe.
Dangerous vibrations.
Right.
Okay. And sound intensity uses that decibel scale.
Yes, the decibel dB scale.
Yeah.
Because the range of sound intensities our ears can handle is absolutely enormous, from incredibly faint to painfully loud, a linear scale wouldn't be practical. The decibel scale is logarithmic.
Logarithmic.
Yeah.
So a small change in dB means a big change in actual intensity.
Exactly. Every 10 dB increase represents a 10-fold increase in sound intensity. It compresses that huge range into manageable numbers.
Okay. Decibels for sound intensity. Now let's talk about the air itself, the atmosphere aircraft fly through. What's it made of?
The atmosphere is a mixture. It's mostly nitrogen gas, about 78%, and oxygen gas, about 21%.
Nitrogen and oxygen dominate. What else?
There's about 1% argon, then tiny amounts of carbon dioxide, neon, helium, and other trace gases. Plus, there's always some water vapor and variable amounts of tiny particles like dust, pollen, salt.
A complex mixture. Does the composition change with altitude?
The proportions of the main gases stay pretty much the same up to quite high altitudes, maybe 50 miles or so, but the overall density drops off very rapidly as you go up.
Less air the higher you go.
Much less. Eventually, it gets so thin that you can't breathe, and engines can't run because there's not enough oxygen for combustion.
Okay. Are there distinct layers in the atmosphere?
Yes, it's generally divided into layers based on how temperature changes with altitude. The lowest layer, where we live and where almost all weather happens, is the troposphere.
Troposphere. Temperature drops as you go up.
Generally, yes. It extends up to about 7 miles at the poles, maybe 10, 12 miles at the equator. Above that is the stratosphere.
Stratosphere. What's key there?
The ozone layer is in the stratosphere. Ozone absorbs ultraviolet radiation from the sun, which actually causes the temperature to increase with altitude in this layer.
Temperature goes up in the stratosphere.
Okay.
Higher layers.
Above the stratosphere are the mesosphere. Temperature drops again.
Yeah.
Then the thermosphere, temperature rises dramatically due to absorption of high-energy solar radiation. And finally, the exosphere, which just fades out into space. There's also the ionosphere, a region overlapping the upper mesosphere and thermosphere, where gases are ionized by solar radiation.
Troposphere, stratosphere, mesosphere, thermosphere, exosphere. But for planes, the troposphere and lower stratosphere are most important.
Absolutely. That's where almost all flying occurs.
And this atmosphere exerts pressure. Atmospheric pressure.
Yes, it's simply the pressure caused by the weight of all the air sitting above any given point.
The weight of the air column above you.
Exactly. At sea level, as we said, it averages about 14.7 psi or 29.92 inches of mercury.
Then it decreases as you go up.
Definitely. Less air above you means less weight, so less pressure. We measure it with barometers, either the mercury type or, more commonly now, aneroid barometer.
Aneroid, what's that?
It uses a small, sealed metal cell that expands or contracts as the outside air pressure changes. This movement is linked mechanically to a needle or a digital display. Aircraft altimeters are essentially sensitive aneroid barometers calibrated to show altitude instead of pressure.
Altimeter measures pressure to figure out altitude. What's the pressure at, say, 10,000 feet?
Standard pressure at 10,000 feet is about 10.1 psi, or around 20.58 inches of mercury, significantly less than at sea level.
Okay, and density also decreases with altitude.
Yes, and this is crucial for aviation. Density is affected by both pressure and temperature, according to the gas laws. As you go up, pressure drops faster than temperature in the troposphere, so the density decreases significantly.
Lower density means less air for the wings to push against, less air for the engines.
Exactly. It impacts lift, drag, engine power, everything. That's why we use the concept of density altitude.
Density altitude, what's that?
It's a way to express the effective altitude based on the actual air density at a given location and time. On a hot day, or at high elevation, the air is less dense than standard. The density altitude might be much higher than the actual field elevation.
So the plane performs as if it were at that higher density altitude.
Precisely. It's a critical calculation for takeoff and climb performance, especially on hot, high, or humid days.
Humidity affects density too. Does water vapor make it denser or less dense?
Less dense, actually.
Really? Water feels heavy.
It does, but a water molecule, H2O, is actually lighter than the average air molecule, which is mostly N and O. So when water vapor replaces some of the dry air molecules in a given volume, the overall density of that moist air decreases.
Less dense air when it's humid. Good to know. And this water exists as vapor, but also clouds and fog.
Yes. The troposphere is rarely perfectly dry. You have invisible water vapor, humidity, and when that vapor condenses, you get visible moisture like clouds or fog, which are just tiny suspended water droplets or ice crystals.
Okay. Does humidity affect engines?
It can. For piston engines, the less dense air means slightly less power for a given throttle setting. Also, the water vapor displaces some oxygen needed for combustion. Sometimes, though, in high-performance supercharged engines, the cooling effect of water vaporizing in the cylinder can slightly reduce the risk of detonation, which is interesting.
Complex effects.
Yeah.
And vapor pressure.
That's just the portion of the total atmospheric pressure that is due to the water vapor present in the air. It's directly related to the dew point temperature.
Okay, now to compare aircraft performance fairly, we need a baseline, the standard atmosphere.
Exactly. The standard atmosphere provides a defined set of reference conditions for pressure, temperature, density, and gravity at various altitudes, starting from sea level.
What are the standard sea level values?
Standard sea level pressure, P euro, is 29.92 inches of mercury. Standard temperature, T, is 15 degrees Celsius or 59 degrees Fahrenheit. Standard gravity, G, is 32.174 feet per second squared.
Okay, 29.92 Hg, 15 degrees C, 59 degrees Fahrenheit. That's the benchmark everyone uses.
Yes. Allows for consistent comparison of performance data worldwide. The U.S. standard atmosphere aligns with the ICAO, International Civil Aviation Organization, standard.
All right. We've covered matter, energy, forces, fluids, sound, the atmosphere. Now let's finally put it all together and talk about the theory of flight for aircraft.
Right. Basic aerodynamics. Understanding this is obviously key to knowing how planes work. It starts with the 4 fundamental forces acting on an aircraft in flight.
4 forces. Let's name them.
You have lift, the upward force primarily from the wings. Weight, the downward force due to gravity acting on the aircraft's mass. Thrust, the forward force from the engines or propeller. And drag, the backward force, resisting the motion through the air, mainly from friction and pressure differences.
Lift, weight, thrust, drag. Always acting.
Always. And they're all measured in pounds, or newtons. The state of the aircraft's motion depends on how these forces balance.
What happens if they're balanced? Lift equals weight, thrust equals drag.
Then the aircraft is in equilibrium. It will maintain a constant velocity, constant speed and direction, and constant altitude. Unaccelerated flight.
And if they're unbalanced? If thrust is greater than drag?
The aircraft accelerates forward. If lift is greater than weight, it climbs. If drag is greater than thrust, it decelerates. If weight is greater than lift, it descends.
Simple cause and effect based on the balance of forces. Now, we talked about Bernoulli's principle for lift in subsonic flight. Can we recap that quickly?
Sure. Remember, Bernoulli says faster-moving fluid has lower static pressure. The airfoil shape makes air go faster over the top surface,
Right, longer path.
so you get lower pressure on top compared to the bottom. This pressure difference creates the upward lift force. We also talked about converging and diverging ducts.
Converging speeds up flow, lowers pressure. Diverging slows down flow, raises pressure.
Yeah.
Subsonically.
Exactly. The wing's upper surface acts sort of like the top half of a converging, diverging passage for the air flowing over it. The total energy, kinetic from speed, potential from pressure, stays constant along a streamline.
So lift comes from that pressure difference, which comes from the speed difference caused by the wing shape. Can we also explain lift using Newton's laws, action-reaction?
Absolutely. It's another perfectly valid way to look at it. As the wing moves through the air, its shape and angle are designed to deflect air downward.
Adjusting air down.
Right, that's the action. According to Newton's third law, the reaction is the air pushing the wing upwards with an equal and opposite force. That upward force is lift.
Action. Wing pushes air down. Equals reaction. Air pushes wing up.
Exactly. You can even use Newton's second law here. The lift force is related to the mass of air being deflected downwards per second and the acceleration, change in downward velocity, given to that air.
So Bernoulli, pressure difference, and Newton, deflecting air, are just two ways of explaining the same thing.
They really are. They describe different aspects of the same physical phenomenon that results in lift. Both are correct and useful perspectives.
Okay, good. Now let's talk more about that wing shape, the airfoil.
An airfoil is just any surface designed to get a useful reaction from the air moving over it. Wings, propeller blades, helicopter rotor blades, even fan blades in a jet engine are all airfoils.
Designed to produce lift or thrust. Key terms for describing an airfoil.
Okay, we have camber, which is the curvature of the top and bottom surfaces. Usually the top surface has more camber.
Or curve on top.
Then there's the chord line, a straight line from the very front edge, the leading edge, to the very back edge, the trailing edge.
Leading edge to trailing edge.
And crucially, the angle of attack. That's the angle between the chord line and the direction the air is coming from, the relative wind.
Angle between chord line and relative wind.
A relative wind is just the airflow direction as experienced by the wing, which is opposite to the aircraft's flight path. Increasing the angle of attack generally increases lift, up to a point.
Up to a point, the stall point.
Exactly. We'll get to that. The camber, especially the upper camber, helps accelerate the flow over the top, creating that low pressure via Bernoulli.
Got it. What about the overall shape of the wing viewed from above? The planform.
Wing planform matters too. Wings can be rectangular, elliptical, tapered, narrower at the tips, swept back like on jets, delta-shaped. Each has different aerodynamic properties.
Different shapes for different speeds or rolls. And aspect ratio.
Aspect ratio is the ratio of the wingspan, tip-to-tip distance, to the average chord, average width. Long, skinny wings, like on gliders, have a high aspect ratio.
And that's good for...
High aspect ratio generally means lower induced drag. That's drag created as a byproduct of generating lift. So more efficient, especially for gliding or long-range flight.
Okay. What about angle of incidence and washout?
Angle of incidence is the fixed angle the wing is mounted to the fuselage at. It's built in by the designer.
Fixed angle and washout.
Washout is a twist built into the wing. The angle of incidence is slightly lower at the wingtip than at the wing root, near the fuselage.
Why twist the wing?
It's a safety feature. It makes the wing root stall before the wingtip at high angles of attack. Since the ailerons for roll control are out near the tips, this ensures you still have some roll control even as the wing starts to stall.
Clever design. Stall the inside first. Okay, let's talk about that stall. It relates to the boundary layer, that thin layer of air right on the surface.
Yes, absolutely. The boundary layer is where the air slows down due to friction with the wing's surface. Right at the surface, the air is stationary relative to the wing.
Starts smooth, then gets messy.
Sort of. Initially, near the leading edge, the flow in the boundary layer can be very smooth and orderly. That's laminar flow. But as it moves back, or as speed or angle of attack increases, it can transition to turbulent flow, chaotic, swirling.
Turbulent flow means more drag.
Yes, more skin friction drag. But the bigger problem is flow separation. If the angle of attack gets too high, even the turbulent boundary layer can't stick to the sharply curving upper surface anymore. It separates.
The flow breaks away from the wing.
Right. And when that happens, the low pressure region on top collapses, lift decreases dramatically, and drag increases sharply. That's an aerodynamic stall.
Loss of lift. Not good. Are there ways to control this boundary layer, delay the stall?
Yes, several methods are used for boundary layer control. Wing leading edge slots are fixed openings that duct high-pressure air from underneath the wing to the top surface, just behind the leading edge.
What does that do?
That blast of high-energy air re-energizes the boundary layer on top, helping it stay attached at higher angles of attack.
Okay. Other methods.
Sometimes air suction is used, literally sucking the slow-moving boundary layer air away through tiny holes in the wing skin. Vortex generators are another common one.
Vortex generators.
Little fins on the wing.
Exactly. Those little vanes create tiny, energetic vortices, swirls, that mix the faster air from outside the boundary layer with the slower air inside it, again helping to delay separation.
Mixing the air to keep it attached. Are there movable devices too? Slats?
Yes, leading-edge slats are basically movable slots. They extend out from the leading edge at low speeds or high angles of attack to open up a gap, doing the same job as fixed slots, improving lift and delaying stall.
Slots, suction, vortex generators, slats. Lots of tricks to manage that boundary layer. Okay, now let's talk flight controls. How does the pilot actually make the plane go where they want? 3 axes. Pitch, roll, yaw. Let's start with pitch, nose up, down.
Pitch is rotation around the lateral axis, the one running wingtip to wingtip through the center of gravity.
Okay. Controlled by primarily the elevator. That's the movable surface on the trailing edge of the horizontal stabilizer, the small wing at the back.
How do they work?
If the pilot pulls back on the control stick or yoke, the elevator deflects upwards. This creates a downward aerodynamic force on the tail.
Pushes the tail down.
Right, which pivots the aircraft around the CG, making the nose pitch up. Pushing forward deflects the elevator down, pushes the tail up, and makes the nose pitch down.
Simple hinge action changes the plane's angle. What's a stabilator?
Some planes, instead of a fixed stabilizer and a moving elevator, have the entire horizontal tail surface pivot as one piece. That's a stabilator. Does the same job.
Okay. And ruddervators on V-tails.
Right. On planes with a V-shaped tail, the two surfaces combine the function of both rudder for yaw and elevator for pitch. They move together for pitch and differentially for yaw.
Clever combination. So pitch controlled by elevator stabilator via yoke stick. No, roll banking left-right.
Roll is rotation around the longitudinal axis, running nose to tail through the CG.
Okay. Controlled by
Ailerons. These are movable surfaces on the trailing edges of the main wings, usually out near the tips.
ailerons. How do they work?
They work in opposition. If the pilot turns the yoke or moves the stick to the right aileron goes up and the left aileron goes down.
Opposite movement. Why?
The upward aileron decreases lift on that wing, the right wing. The downward aileron increases lift on the other wing, the left wing. This difference in lift creates a rolling moment.
So right yoke makes the right wing drop and the left wing rise, causing a roll to the right.
Exactly. And turning the yoke left does the opposite left aileron up, right aileron down, rolls the plane to the left.
Differential lift on the wings causes the roll.
Okay.
Finally, yaw nose moving left-right.
Yaw is rotation around the vertical axis, straight up and down through the CG.
Vertical axis, controlled by...
The rudder. That's the movable surface on the trailing edge of the vertical stabilizer, the tail fin.
Rudder controls yaw. How? With pedals.
Yes, controlled by rudder pedals at the pilot's feet. Pushing the right pedal deflects the rudder surface to the right. This creates an aerodynamic force that pushes the tail to the left.
Tail left.
Which makes the nose yaw to the right. Pushing the left pedal does the opposite, yawing the nose left.
Okay. Do pilots use rudder much in turns? I thought turns were mostly ailerons.
They use both together in a coordinated turn. When you use ailerons to bank, the wing that goes down actually creates a bit more drag temporarily, which can cause the nose to swing slightly opposite the direction of the turn. That's called adverse yaw.
Ah, the nose lags behind.
Right. So the pilot uses rudder in the direction of the turn to counteract that adverse yaw and keep the nose smoothly following the turn arc. Ailerons initiate the bank, rudder keeps it coordinated.
A coordinated dance between ailerons and rudder.
Okay. We also mentioned supplemental lift devices earlier. Flaps.
Yes, flaps are probably the most common. They're usually on the trailing edge of the wings, inboard of the ailerons.
What do? When extended, they increase the wing's effective camber and often its area, which significantly increases lift, especially at lower speeds. They also increase drag.
More lift and more drag. Good for takeoff and landing.
Exactly. Allows the plane to fly slower without stalling, making takeoff shorter and landing slower and steeper. There are different types: plain, split, slotted, Fowler, each work slightly differently.
And leading edge devices. Slots and slants again.
Right, we mentioned them for boundary layer control, but they're also considered high lift devices because by delaying the stall, they allow the wing to operate effectively at higher angles of attack, which means more lift.
So flaps, slots, slats all help generate more lift at low speeds. Okay. Now, what happens when planes go really fast? Approaching and exceeding the speed of sound. High-speed aerodynamic use that air becomes compressible.
That's the key difference. Below about Mach 0.8, 80% the speed of sound, air mostly behaves as if it's incompressible. But as you get closer to Mach 1, the air starts to pile up in front of the plane, and its density changes significantly as it flows around the surfaces. It becomes compressible.
And that changes the rules.
Yeah.
Like with converging, diverging ducts.
It completely reverses the rule for supersonic flow. Remember, subsonically, a converging duct speeds up flow and drops pressure. Supersonically, a converging passage slows down the flow and increases pressure and density.
Wow, opposite effect. So supersonic planes need different shapes.
Absolutely. Thinner wings, often sharply swept back or delta-shaped, sharp leading edges, all designed to manage compressibility effects and the formation of shockwaves.
Shockwaves.
Yeah.
That happens around Mach 1, the sound barrier.
Well, the speed of sound isn't really a barrier, but it is a critical speed. Pressure disturbances propagate through air at the speed of sound, about 761 miles per hour at sea level standard conditions.
So as the plane approaches that speed,
The pressure waves it creates can't get away fast enough in front of it, and they start to coalesce into a shock wave.
okay, what happens in transonic flight around Mach 0.8 to 1.2?
That's a tricky regime because parts of the airflow over the aircraft might be subsonic, while other parts, like over the top curve of the wing, become supersonic.
Mixed flow speeds.
Right, and where that supersonic flow has to slow back down to subsonic, a strong shock wave, called a normal shock wave, perpendicular to the flow, often forms.
And that's bad.
It can be. Shock waves cause a sudden increase in pressure and temperature, a decrease in velocity, and often lead to airflow separation just behind the wave. This separation dramatically increases drag and can cause a loss of lift and stability problems. The center of lift can shift abruptly rearward, causing the nose to pitch down.
Mach tuck.
Mach tuck.
Sounds serious. The speed where this starts is the critical Mach number.
Yes, the critical Mach number is the speed at which the air flow somewhere on the aircraft first reaches Mach 1 and shock waves begin to form significantly.
Okay, and fully supersonic flight. Above Mach 1.2.
Then the entire airflow around the plane is supersonic. Shock waves are still present, but they are typically attached to the nose, leading edges, and trailing edges, and are often oblique, angled, rather than normal. Hypersonic flight is generally considered to be above Mach 5.
Okay, shockwaves are key. Can you explain them a bit more? What are they physically?
A shock wave is an extremely thin region where the properties of the air pressure, temperature, density change almost instantaneously. It's formed by the constructive interference, the piling up, of all the pressure waves created by the object moving at or above sound speed.
Piling up of sound energy. And if they reach the ground, we hear a sonic boom.
Exactly. It's the abrupt pressure change hitting your ear. We mentioned normal shock waves, perpendicular to flow, usually in transonic flight or ahead of blunt objects. Behind a normal shock, the flow is always subsonic and pressure temperature jump up.
Okay, and oblique shocks.
Oblique shock waves are angled relative to the flow. They form on sharp leading edges and cones in supersonic flight. The flow behind an oblique shock can still be supersonic, though slower, and the pressure jump is less drastic than across a normal shock. Supersonic airfoils also generate expansion waves where the flow turns around a convex corner, causing pressure to drop.
So the shape of the shockwaves changes as speed increases.
Definitely. As an aircraft accelerates through the transonic regime, shock waves first form on the upper wing surface, strengthen, move rearward, and eventually, in fully supersonic flight, you get attached oblique shocks at the leading and trailing edges, assuming the wing is designed for it. Managing these shock waves and the associated drag and stability changes is the main challenge of high-speed flight.
Fascinatingly complex. Okay, let's shift completely now to helicopters. Rotating wings. Very different aerodynamics.
Very different in many ways, yes. The main rotor blades are essentially rotating wings generating lift. Key terms are a bit different. Blade pitch is the angle of the blade relative to the rotational plane.
Okay, pitch angle.
Blades also flap. They move up and down on hinges, flapping hinges, as they rotate. This is crucial for compensating for differences in lift between the advancing and retreating sides of the rotor disc in forward flight.
Flapping hinges for lift symmetry.
What else? They also move fore and aft slightly in the plane of rotation on drag hinges, also called lead lag or hunting hinges. This relieves stresses caused by the changing aerodynamic forces during rotation. Blade pitch itself is controlled by pitch change rods linked to a swash plate mechanism below the rotor hub.
Flapping, lead lag, pitch change. Are all rotor systems the same?
No, there are different types. Fully articulated systems have hinges allowing all three motions, flap, lead lag, pitch change, independently for each blade. Semi-rigid systems usually have two blades rigidly connected, teetering like a seesaw to allow flapping, with independent pitch change. Rigid rotor systems have no flapping or lead leg hinges. The blades themselves are designed to flex to accommodate these movements.
Different mechanical designs. How do helicopters control yaw? No rudder back there usually.
They need something to counteract the torque from the main rotor wanting to spin the fuselage in the opposite direction. Most use an anti-torque rotor, or tail rotor.
The small propeller on the tail.
Right. It pushes air sideways to counter the main rotor torque. It's controlled by anti-torque pedals in the cockpits, similar to rudder pedals. Some helicopters use no-tar, no-tail rotor systems, which use ducted fan airflow vented out the tail boom instead.
Okay, tail rotor or no tar for yaw. How about roll and pitch? Moving backward, sideways.
That's controlled entirely by the main rotor disc. The pilot uses two main controls, the collective and the cyclic.
Collective and cyclic, what do they do?
The collective pitch control changes the pitch angle of all the main rotor blades simultaneously by the same amount. Increasing collective pitch increases overall rotor thrust lift, making the helicopter climb or hover. Decreasing it makes it descend.
Collective up, down. What's the cyclic?
The cyclic pitch control tilts the entire rotor disc. It does this by changing the pitch of each blade cyclically as it goes around the rotation. For example, to tilt the disc forward, the cyclic makes the blade pitch decrease as it passes the front and increase as it passes the back.
Tilts the disc by changing pitch individually around the circle.
Exactly. Tilting the rotor disc forward directs the thrust slightly forward, making the helicopter accelerate forward. Tilting it sideways makes it roll and move sideways. So cyclic controls direction.
Clever mechanism. What's translating tendency?
Because the tail rotor is pushing sideways to counteract torque, it also creates a sideways force on the whole helicopter, making it want to drift. This is translating tendency. Pilots usually compensate by slightly tilting the main rotor disc with the cyclic, called cyclic feathering, or the whole transmission might be rigged slightly offset.
Okay. And dissymmetry of lift. Sounds like a problem in forward flight.
It is, but it's compensated for. In forward flight, the rotor blade moving forward, the advancing blade, experiences a higher airspeed, its rotational speed plus the helicopter's forward speed, than the blade moving backward, the retreating blade.
Higher speed means more lift, right, from Bernoulli.
Right, so the advancing blade wants to generate much more lift than the retreating blade. This asymmetry would cause the helicopter to roll over if not corrected.
How is it corrected?
Primarily by blade flapping. The advancing blade with this higher lift naturally flaps upward. This upward motion reduces its angle of attack, decreasing its lift. The retreating blade flaps downward, increasing its angle of attack and increasing its lift.
So flapping automatically balances the lift across the rotor disc.
Largely, yes. It's a fundamental part of how most helicopters work.
Okay. But there's a limit. Retreating blade stall.
Yes. At high forward speeds, the retreating blade's relative airspeed gets very low. To generate enough lift to match the advancing side, its angle of attack, increased by flapping down and cyclic input, has to become very high. Eventually, it can exceed the critical stall angle.
The retreating blade stalls.
Yes. This causes vibration, lift loss on that side, and an unstable pitch-up moment. Retreating blade stall limits the maximum forward speed of conventional helicopters.
A fundamental speed limit. What about auto rotation? Engine failure procedure.
Auto rotation is amazing. If the engine fails, the pilot immediately lowers the collective pitch. As the helicopter descends, the airflow now comes up through the rotor disc instead of down.
Airflow reverses direction through the disc.
Right. And this upward airflow keeps the rotor blades spinning, like a windmill. The helicopter essentially becomes a gyrocopter or autogyro.
The blades keep turning without engine power.
Yes. The pilot uses the stored rotational energy, inertia in the blades, and controls the descent rate with the collective, uses cyclic to maintain forward speed for control, and then flares near the ground, using the collective again at the last moment to cushion the landing. It allows for a controlled landing even without engine power.
Incredible safety feature built into the physics. Okay, helicopters are complex. What about simpler flying machines like weight shift trikes and powered parachutes?
Right. Weight shift control aircraft, or trikes, typically have a hang glider-like fabric wing mounted above a wheeled carriage with an engine.
How are they controlled? No ailerons or rudder.
No. Control is entirely by shifting the pilot's weight relative to the wing using a control bar. The bar is connected to the wing structure. Pushing the bar forward tilts the wing leading edge up, increasing angle of attack for climb. Pulling it back lowers the nose.
Shifting weight changes the wing's angle. How about turns?
You push the control bar sideways, this banks the wing and the aircraft turns, with the carriage and pilot swing like a pendulum under the wing. Very intuitive once you get the hang of it.
Weight shift for all control. And powered parachutes. They look like a parachute with a fan on the back.
Pretty much. It's a flexible fabric wing, like a paraglider wing, attached to a carriage. The wing isn't rigid. It's inflated into shape by the airflow from the propeller and the forward motion ram air inflation.
Inflated by air. How do they fly?
Once the wing inflates and generates lift, usually around 28-30 mile per hour airspeed, the aircraft takes off. Climb and descent are controlled purely by engine throttle.
Throttle for up-down. How do they turn?
Turning is usually done with foot pedals or steering bars that pull down on the trailing edge of one side of the wing. This increases drag on that side and changes the lift slightly, causing the aircraft to yaw and bank into a turn. Very simple controls.
Simpler machines, different aerodynamics. Okay, well that covers an amazing range of physics principles that all come together in aviation.
It really does. From the very basics of matter and energy, force and motion, all the way through fluid dynamics, thermodynamics, sound, and the specific aerodynamics of different types of aircraft. It's all interconnected.
And having a grasp of these fundamentals is just crucial for anyone working with aircraft, whether maintaining them or flying them.
Absolutely essential. Understanding why things work the way they do makes you safer and more effective.
It really makes you appreciate the ingenuity behind flight. Seeing how these physical laws are harnessed, it's quite something. This has been a really thorough grounding in the physics underpinning aviation.
We've covered a lot of ground, definitely. And really, each of these topics could be a whole discussion in itself. There's always more depth to explore.
For sure. Something for our listeners to perhaps ponder is which of these principles seems the most counterintuitive or surprising when applied to making something so heavy fly. Definitely food for thought. Thanks for walking us through all that.
My pleasure. It's fascinating stuff.